So let's talk about functions in section 9a. Um, and you can take a look at this YouTube video and watch through this. But what we're going to talk about is here where it says a function describes how a dependent variable changes with respect to one or more independent variables. So it says when there are two variables, they're often summarized as an ordered pair with the independent variable first. So it's an ordered pair has the parentheses, and then you'll see the first coordinate, comma, the second coordinate. So the independent and then the dependent. Typically, we call x the independent and y the dependent. It says the dependent variable is a function of the independent variable. And if x is independent and y is dependent, then we can write it as y is a function of x. We have some examples that follow, so let's talk about these examples. If we have, let's go down to this one. The total distance a person runs after various amounts of time during a morning jog. So let's pause the video and you pick out what you think the two variables are here. All right, so the two different variables here are the distance and the time. So let's highlight them in the top. So we've got the distance, the total distance that a person's going to run after a various amount of time. So when we think about this, the time that you spend running will cause your distance to either increase or decrease. So as the time increases, so if you're running for a long amount of time, the longer you run, the longer the distance that you run. So if we were to discuss this as a linear relationship, as the time increases, the distance increases. And so we would say that the distance that I run depends on the time. And when you talk about this, you always think of the dependent variable depends on the independent variable. So this is my y. My y depends on x. So time is my x, or my independent, and distance is my y. So to write it as an ordered pair, I would say time, comma, distance. Let's look at Roman numeral 2. Roman numeral 2 discusses three basic ways to represent a function. So you can look at a data table. You can represent a function with data table. You can have a picture or a graph drawn, or you can write an equation. Those are three different ways that we see functions. And when we talk about functions, we talk about their domain and their range. The domain is the set of values that represent the independent variable. The domain is the set of all possible x values. The range is the set of the y values. They represent the dependent variable. So in this example that follows, here we have the time and the temperature. This is the temperature data for 12 hours, reading the top of the table. And so the time goes from 6 a.m. to 6 p.m. and the temperature, let's see, the lowest looks like it would be 50. And then it goes up to 73. And so The temperature depends on what time of day it is. When it's early in the morning, you usually see a lower temperature. When it reaches mid-afternoon, you see the highest temperature of the day when the sun is out at its fullest. So you see that they write the x, comma, y, they write it as time, comma, temperature. And it says, based on this data that you see here, negative values of time do not make sense. Time would only, in this case here, we're talking about from 6 a.m. to 6 p.m. When we're dealing with time, you can't go back in time. So we don't have negative values of time. And the temperature goes from 50 to 73. So if we want to, so this is an example of a function represented with a table. And then down below, we see the same data put into a picture or graph. And they show you two graphs here, and we're asked ourselves, which one is the best graph for this data? And I would say, and so they also, instead of using 6 a.m., 7 a.m., 8 a.m., they represent the hours since 6 a.m. So you have 2 hours since 6 a.m., that would be 8 a.m. 12 hours since 6 a.m. would be 6 p.m. And so when you take a look at these two graphs, when I look at them, which one's the better representation? Well, it would be this one here on the right-hand side, because it's zoomed in. These quadrants here are not important or relevant to that table. So yeah, you can graph it either way, but probably this one would be the best representation of it. And so and here we just have the points plotted. But realistic, if we go down, realistically, every time throughout the day, if we're talking about 12 p.m., 1 p.m., there is temperature in between. So we can draw a line connecting the points like you see here. And the graph is now the model you can use to predict the temperature at any time of the day. So if you say, what is 5.5 hours since 6 a.m., well, that would be 11:30. What temperature is it at 11:30? Here we can see between 11:30, it should be between 65 and 70. And with the graph, we can kind of see that. You can, if you have graph paper and an accurate description, you can see that it would be 67 degrees. So let's continue to scroll through here. And this Roman numeral 4 here talks about creating and using graphs. So we've got some steps here. And when you are looking at trying to create the graph, so here the graph was created for you, but when you're looking to create the graph, what you should do is identify the independent and dependent variables, which is what we did originally. We looked at the table and we decided which one depends on what, and that's what you put on each axis. And then you identify, when we looked at this table, we said, okay, well, the time goes from 6 a.m. to 6 p.m., or you could say 0 to 12 hours since 6 a.m. And the temperature goes from 50 to 73. So you'll see that the graph here is doesn't start at 0, it starts at 50. 50 to 75, because that's my region of interest. And if I started at 0, then it kind of zooms it out so much that it's harder for me to read. So you want to zoom into your region of interest to make the graph easier to read. And notice how when you're in between here is 5 degrees, but the in between here is more than 5 degrees, it's 50. And so they put this little mark here to show that there's a break in the graph there and that this is zoomed in. And then you plot the points, and then you connect with a line. And then step 4 would be to make a prediction if necessary, and kind of also ask yourself, does it make sense because this is the data from 6 a.m. to 6 p.m., would it be accurate for me to say, because this line is going downward, should I decide after this time period that I can accurately predict? So usually you want to use only the predicted models from here, like between the 6 a.m. and 6 p.m. and not go outside. So those 4 steps are given to you on this next page. And so you have an example that you can try here where you have the altitude and pressure, and you use those 4 steps to sketch your graph. And then so from this table here, you should try looking at the altitude and pressure. The pressure is dependent on the altitude, so you're going to put the altitude on the x-axis, and you're going to put pressure on the y, and then you're going to sketch your graph, and then you can check your results with the filled in paper from this section. What I want to take a look at is this last part, and let's use the last few minutes here to discuss this last part. So here we have the price of a car. Initial price is $23,000, and it decreases $2,500 each year. So the equation is written right here, and let's talk about this equation. So on the formula sheet, we have the dependent variable is equal to the initial amount plus the rate of change, or the slope, times the independent. And just from this, a couple sentences here, the price of the car was initially $2,300. So this is the initial amount. The car decreases in price by $2,500 every year. So the initial amount is $2,300. That's going to go here. The 2 different variables in this are the price of the car and the number of years. So we've got the number of years is going to be, the price of the car is going to depend on the number of years. So the number of years is going to be our independent variable, which you see represented with T here. And the dependent variable is going to be the price of the car. So this right, the dependent variable is the price of the car. And you see that represented with capital P. So you've got the initial amount, $2,300, and how much does it go down each year? It goes down 25. I'm sorry, I said the initial price is 23,000. Sorry. The price that goes down each year is 2,500. And so that is the rate of change. Each year it decreases by 2,500. So year 1, it's one year after you purchase it, it's going to be 2,500 less. Year 2, it would be 2,500 times 2, or 5,000 less. And that is represented here. And why is there a minus sign though? There's a minus sign here because it decreases. So decreasing means I'm going to do subtraction. So it's decreasing 2,500 times the number of years. And so this, going on Desmos is a website you can go to and you can graph something. And so they put in this equation in Desmos and they get this graph out of there. And an excited classmate says, hey, look, since the line goes on forever, the price, we can plug in any number for T and find the price. And does the model work for any value of T? And the answer here is it works in this range. You can't go back in time, and so you can't go negative time. And after a certain point right here, the price of the car is not going to be negative. It doesn't make sense for a car to be a negative value. So between 0 and what looks to be 9, we have prices, but after that range, it doesn't make sense. So the domain here, when you talk about domain and range, the domain would be from 0 to 9, and the range would be from 0 to 23,000.